Hi everyone, welcome back to my video on control systems. In this video, I'm going to explain about this concept of the lead lag, and I'm going to talk with this application of using a prefilter to enhance our design. Let's assume one trivial example to illustrate the usage. Now let's assume that you are given a plant like this, so it can be anything, and for the sake of the explanation, let's just take it as a simple. You are looking at the motor. So this motor here is having a second order transfer function of 1 over s plus 1 multiply s plus 4. And then this is the input, and then you are having the output, and the output will be in terms of the rotational speed. And as usual, we will have a subbing point here, and then this whole thing here are connected in the form of the feedback. And of course, the rotational speed over here will actually adjust in response to your set point. And then your set point should be also some quantity that directly relates to the rotational speed. Now let's just use MATLAB to illustrate the entire application over here, and what can we do actually to improve the system's performance. We will define the transfer function G as what we have seen earlier, which is basically a 0 pole gain with no 0, and then 2 poles, -1 and -4, and then I have a gain of 1. Here I have generated the step response of the system, so let's look at it. I will have a setting time of approximately about 3.18 seconds, and then I am going to look at the steady state error of 0.2, which is the final value. And then taking into a consideration of a unit step input, I will consider it to have a very large error, because the output value for zero steady state error should be 1. Now we look at here, as I mentioned earlier, that this steady state value, it is not very good. And then the settling time 3.18 seconds also is somehow just a mediocre system. So imagining that if you are actually running a motor and it takes about 3.18 seconds so that the system can only settle at its steady state, so it is actually considered quite slow. Now let's try to improve it. If let's say the idea is that we just want the final value to have closer to 1, which means that the system would have a lower steady state error, and I just don't really much care about the settling time. I just want to make the system goes faster. So what can I do here is that the simplest way is to actually increase the gain, because we know that for normal systems, as long as we increase the forward gain, our final value will become better if I increase the forward gain. But for this system, this is a pure second order system without any zero. What we observe over here, it is if let's say this is the root locus, I'm going to have 2 points here, which is -1 and -4. And then basically this will be how the root locus looks like. So I can see that actually, if let's say this is a point of -2.5, if I try to increase my gain, what happened here is that my roots will be running from this point, go to here, and then go up. Of course, the other complex conjugate will actually go down in the other direction. But I can see that actually the settling time here will be actually equals to 4 over 2.5, which no matter how large the gain, if you keep on increasing, the settling time will still remain unchanged. That means even though if I can improve the final value here by increasing the gain, the forward gain, my settling time can only go to a max of 4 divided by 2.5. So let's try to verify this using the simulation, and we see that our hypothesis whether is it correct or not. Now let's calculate our settling time TS to be equals to 4 over 2.5. It is actually 1.6 seconds. I repeat this, but I am actually changing my forward gain to, let's say, something like 1000. I check here, my setting time, roughly about 1.6. Although I can see that now, my final value is actually approaching to 1, which is a result of a much incremented gain, but my settling time cannot be improved further. It will start at approximately 1.51, or you can say approximately 1.6 that we calculated based on 4 divided by 2.5. So we come back to the root locus of the original uncompensated system, whereby this will be the shape of the root locus. And then if I want to improve this, okay, other than incrementing the gain to actually compensate for the low steady state performance, okay, and I also wish that if I can increase the gain, I will be able to make the system goes faster. So to go for the system to go faster, basically I will need the root locus to actually bend towards to the left hand side. So by bending it to the left hand side, I am actually setting my zeta omega n value to be higher. If the zeta omega n value to be higher, which is my settling time to be 4 over zeta omega n, and if this goes up, my settling time will goes down. How do I make sure that the root locus can bend towards to the left hand side? The answer is very simple. We have covered it earlier in the lead compensator. We just add a lead compensator, whereby I basically add a pole and 0 here, and these two will come from my lead compensator. And since this is just a very trivial example, I will not be answering a very strict or stringent requirement. So let's just add some points over here in an arbitrary locations. And because our ideal aim is just to illustrate how the prefilter works. Now in this case, I will just simply add anything. Let's say this is minus 25 and this is minus 5, just for the simplicity. So I will add these two, and then we hope that by adding these two, okay, my root locus can bend toward this side, and then hence by increasing the zeta omega n value and thus lowering the settling time. Okay, so let's do this. So I will now be generating a compensator, my lead compensator, to have a 0 at minus 5 and to have a pole at minus 25. And then let's look at the root locus of the system. Now you see that, okay, let's say I sketch some dotted line over here. The dotted line represents our uncompensated system. So this line here, it is the uncompensated system, while the other colored lines here shows that it is the root locus of the compensated system. Okay, and you can see that very clearly that our roots are actually moving towards the left hand side, and hence I can be very sure that by incrementing a certain value of the gain, I can actually move the root locus, the closed loop post to the left hand side of the S-plane, and hence to make the system faster. So faster, which means that my settling time is actually lowered. So let's do this. And to verify, let's say I take one point here and maybe I move to a location which is easier for my calculation. So maybe I just stop at 101 here. So this shows that if you actually apply a gain of 101, I can have a damping ratio of 0.908, which will result us into an overshoot of 0.111%, which is actually quite good because you have still is a very low overshoot. Okay, and then I will have a frequency which is omega n of 5.5. So let's do some calculation over here so that we know what we are going to expect. Okay, we have the overshoot already. The overshoot is 0.111, and I also need to know what is my settling time. Okay, so settling time can be approximate to 4 over zeta omega n. And if you substitute all the values here, which is a zeta equals to 0.908 and your frequency equals to 5.55, we are going to get approximately about 0.8 second. I mentioned over here is an approximated value simply because now we are looking at a third order compensated system, and also we have this 0, which is the actual reason why I want to introduce this video, because the existence of a 0 here will adversely affect our computation or estimation of the transient, especially the transient. So we're going to use the prefilter to minimize the effect, but now let's just assume that we are looking at the system without any 0. That's why we say it's an approximation. So the response, we have a very low overshoot, 0.111%, and rather faster settling time, 0.8 seconds. Okay, so remember just now we said that the uncompensated system, if you use a gain adjustment, the max we can go is actually 1.6 second settling time, and now it is actually double the faster. So let's verify this. So we look at here, I'm going to generate the step response with a feedback system of just now we set the gain, or we encounter the gain of 101, and now I will have the C and G together, the compensator system, with an additional gain of 101. So let's simulate this. Okay, we have this step response, so let's look at the peak response and also the settling time. Now you see that the output response, although it seems like not bad, okay, however, if you notice that the overshoot, just now we have calculated, which is approximately 0.111 as indicated in the root locus diagram, and also our settling time should be close to 0.8, although now it's actually better, but it is actually out of our expectations simply because the existence of the 0. So what I mean by existence of the 0, let's draw the diagram out again. So this is the little guy that I'm mentioning here that will actually affect our calculation. So by multiplying these two and then you close loop it, the closed loop transfer function will have an additional 0 of s plus 5. And this is the guy that actually affects our computation or our estimation. So now, how do we actually eliminate this to make sure that our estimation on the transient response will become better? So what we do here is that we can actually add something what we call as the prefilter. So this prefilter will have the pole s plus 5, which is exactly the same as the 0 here, so that when multiplied together with the closed loop compensated system or the transfer function, this s plus 5 and this s plus 5 can be cancelled with each other. But take note here, by introducing additional pole, it will actually lower down the ratio between the poles and 0, and hence will increase the steady state error. So a good rule of thumb here is that if you add the s plus 5 over here, this guy 1 will also have to change to 5. So that when you actually perform the limit theorem, after you cancel off with the s term over here, it becomes 5 over 5, and then you introduce basically nothing to change the original compensated pole-0 ratio, so that you can maintain your expected steady state performance. So let's do this by introducing the prefilter. So let's our f here to be our prefilter transfer function, which has a gain of 5 and then s plus 5. Now in this step, you see that on top of the feedback transfer function that we have earlier, I'm introducing an additional prefilter in front of it, so that our systems can exhibit the timed response that close to our prediction. So remember, earlier we have predicted that my maximum overshoot should be somewhat close to 0.1%, and then my settling time should be somewhat close to 0.8 seconds. So you can see that clearly now the settling time as opposed to earlier, and also our overshoot as opposed to the earlier result here is getting much closer than what we have predicted. So now you have a choice over here, is that after you have implemented your lead lag controller or other forms of the controller, and if you have identified that actually your 0 is the main cause of the difference between your calculated or estimated values, as opposed to the generated or simulated performance. So you can consider the use of a prefilter to minimize the effect brought by the additional zero introduced while you are designing your controller. So that's all that I want to present in this video. Thank you very much.